You can hear me. Sorry for the delay. So welcome to this live. My name is Clara. If you're seeing this for the first time, I'm a particle physicist here at CERN. And right now I am outside in the Detector Garden here at CERN. It's a beautiful, sunny spring, summer evening. Either way, it's lovely. And yeah, welcome to the live. I'm hoping that everyone can hear me okay. I can see that there's a couple of comments in the chat, but they were here when I arrived, so maybe you can let me know if you can hear me and if where you're joining from. That would be excellent. And yeah, then we can get started and I can show you around the garden and answer any questions that you have about particle physics, about research at CERN. I will do my best. I will let you know though that there are thousands of people working at CERN on different things, so I do my best to answer your questions, but there's always things that maybe I'm not an expert in, and that's just how it works at CERN. Great, so I can see a wave. Thank you so much. I hope that you can hear me okay. I do have a microphone on and I'm hoping it's working because we're going to be walking around a little bit, so I want to make sure that you'll be able to hear me when I walk. But yeah, it's beautiful here. It's lovely and sunny. Nice evening. Great, I get a thumbs up. Thank you so much. Excellent. So yeah, it's good to know where you're joining from. Let me know in the chat. I realize slow-mo is on, so you have to wait 5 seconds between each chat, but hopefully that's not going to be too much of a problem. And we'll get started in a moment. Well, we already are started, but we'll start walking in a moment. Oh, I see the comment now that when I arrived. Thank you so much for the nice comment. Ah, excellent. So someone's joining from near Chicago, about an hour away from Fermilab. So that is, if you didn't know already, that's where I did my master's project. So I did my undergraduate at the University of Manchester in the UK. And as part of my master's project, you have to do some real research to get your master's thesis. And I applied and was selected to work on top physics research with the D0 collaboration at Fermilab. And I did it remotely. So one of the nice things about particle physics is that we can basically access our data anywhere where there's an internet connection. And so a lot of people aren't based at the labs, they're based remotely. And I was able to do my research at Manchester, and then very kindly at the end of my research they offered that I could go to Chicago for 2 months, which was an incredible experience for a master's student to get to go and work at Fermilab for 2 months. And I really enjoyed the international environment, the way of working there, the research, and that's really what then pushed me to want to do a PhD at CERN, because the Large Hadron Collider was turning on at the time that I was doing my master's research, and it actually ended up turning on properly just after I arrived at CERN. But it was a really exciting time. We hadn't yet discovered the Higgs boson. There was so much going on at CERN that I just wanted to be part of it. And so I applied to do my PhD research here at CERN, and then I started working on detector physics, so prototyping of radiation-resistant pixel detectors that were installed in the Atlas detector. And now I've kind of come full circle, because now I work on top physics again. And I also did some machine learning for my master's project all that time ago. So machine learning, AI, that kind of research has been a long-term component of particle physics research. We've really been using it for a long time to analyze the data, because we have so much data that comes from the collisions of the Large Hadron Collider. Oh, and so actually I just see a comment in the chat. How do you distinguish between noise and real particle events in your data? And that's a fantastic question, and is actually linked a bit to some of that machine learning work. So we do it by really precisely understanding the particles that we want to study, and then looking at the data that we have and making selections on what we think is a particle or is noise. And then now we use machine learning for that kind of selection. Almost all of the analyses that we do have a machine learning component to them, because you can generate and create these algorithms where you train them on what a particle would look like in your detector from simulations and then compare it to noise. So you can also simulate the noise in the detector, and then you can really precisely train the machine learning algorithms to be able to distinguish this, and then you put the real data through. But we always know that we're not going to be perfect. That's just a part of the way that we do particle physics. And so it's really a numbers game. We get trillions of events and we stack them all on top of each other in our plots to look at the overall trends in our detector. So we can never say for certain that this is definitely an electron, for example, or this is a Higgs boson in our detector, but we can look at the trends over all of the events. So that's one of the ways that we can do it. So hi, yeah, thanks so much for joining. I see some more people joining in the chat as well. Welcome. If you are not subscribed already, please do subscribe to the channel, because that would really make my day. And you get notified then when I go live on the channel, because I tend to do this quite not randomly, but when I have time and I want to jump on a live and talk to you, that's one of the fantastic things that I can do in these lives, is I can just turn my camera on and show you where I am at CERN and chat with you about the research we're doing. And some of them I will schedule in advance when we get to go underground again, when the Large Hadron Collider is off. But right now it's running, so we cannot go underground. It's just not a good idea when the Large Hadron Collider is running. And so I will just show you around where I am above ground, but when I can schedule them, then I will schedule them as well, so that you get some advance notice and we can go and check out some other things at CERN and talk to my colleagues, because there's lots of incredible people here at CERN doing fantastic work, working on so many different things, and so I want to share as much of that with you as possible. Great. So oh, somebody's asking about the lead to gold experiment conducted at CERN. How much power was used to create all the gold before it dissolved? So honestly, there was no extra power used to create that gold. It's sort of a byproduct of the way that we were doing the experiment. We use lead ions. So usually we use protons in the Large Hadron Collider. We accelerate protons and collide those. But for some weeks of the year, we're colliding ions, and often it's lead ions. And this is so that we can then collide these in the center of our detectors, and it allows us to momentarily recreate the conditions of the early universe and be able to study what those conditions were like when the universe was incredibly hot and dense together. And the gold was a kind of byproduct, because sometimes when these lead ions get very close to each other, there's an interaction, a magnetic, electromagnetic interaction, and the sort of photons that are exchanged can knock some of the protons or neutrons in an ion out of the ion. And in that case, then you're changing the element if you're changing the number of protons in it, and you knock a few out and you get gold. So there was no extra power. It wasn't an intentional thing. It's a very tiny amount of gold, so we don't get to keep it. And unfortunately, it would be so cool to be able to say that this gold came from the Large Hadron Collider and make jewelry, and that would just be so amazing, but it's not something that we can do, unfortunately. So it just gets collided with the side of our detector, or it'll end up somewhere else. But it's such tiny amounts. It's yeah, it's a really small amount, but it's very cool. It's really interesting to learn about this. And one of the important reasons that they did this study is that we need to understand how the beam is moving through the Large Hadron Collider and any losses that we might get in the beam, so that we can make it as efficient as possible. And by understanding when these new elements are made from these close by interactions, then we can better simulate the beam and understand what's going to happen when we do ion collisions. So it's a really important study of how the beam dynamics and how the beam evolution happens. So if I miss your question, please do pop it down in the chat again, because in a moment I'm going to go on a walk around this garden. It's beautiful. I don't know if you can hear the birds, because I don't know if the microphone is picking them up, but it's a really lovely evening. And so then I might miss some of your comments also if I'm not looking at the chat directly. So please do pop them down again. I will try and answer as many as I possibly can. And there's another question down here. How long does the LHC tend to run at a time? It runs on average, I don't know the exact number, but it runs on average about 12 hours at a time. And then we tend to decide to remove the beam from the beam pipe, from the tunnel, and start again with a fresh set of protons, because over time, as the collisions happen, we're losing protons from the collisions and just from generally them being in the accelerator and any interactions that they have. And eventually then the density of protons and the number of protons in the beam gets reduced, and it just becomes inefficient to keep running the Large Hadron Collider. So we can then remove it and we start again, and it takes about an hour or two to go from the canister of hydrogen gas that we start with to then filling the Large Hadron Collider and getting up to the energies that we want to be colliding at. So there's a calculation, and they study then when's the best time to remove the beam from the beam pipe and start again. But sometimes things happen where the beam gets removed automatically by the systems that we have in the accelerator. If any of the not the main detectors, but any of the detectors around the ring notice that maybe the beam is a little bit wobblier than usual, then they'll remove it from the pipe automatically. Or if there's some extra losses, maybe it's hitting into what we call a collimator. So it's a bit of the accelerator that helps the beam be more focused and tidies it up a bit. And if more of the beam is hitting into that, then maybe they'll remove it, maybe investigate, and then fill in again. I don't remember the exact number, but I think our record is something like 56 hours or something like that. And if I remember correctly, it was because one of the pre-accelerators, so the Large Hadron Collider is not the only accelerator that we have at CERN, it's the end of the chain of the main series of accelerators, and then we have other accelerators for other jobs. One of the pre-accelerators was down for a bit, and so we couldn't refill the Large Hadron Collider, so they just decided to keep running with the collisions that they had while they were waiting for the pre-accelerator to get back up running again. So I think it's something like 56 hours, it might be more than that, but it's pretty cool that the Large Hadron Collider could continuously be colliding protons for that amount of time. And then we run for roughly about 8-9 months of the year. It varies every year depending on the Large Hadron Collider schedule, and then we shut down in the winter to be able to do regular maintenance. And then next year we're going to go into what we call a long shutdown as we prepare for something called the high luminosity LHC. And for people like me, I'm really excited about the high luminosity LHC because we're going to install new detector components. We're going to take some bits out of the cavern. We're going to install brand new detector parts that we've been working on for a very long time, which will improve our ability to detect the particles in our detector. And the accelerator is going to get an upgrade, so we're going to get even more collisions at once when those beams cross, and it's just going to give us way more data. So that's very exciting for people like me who just want loads of data so we can look for incredibly rare events in our detector. And so that's going to happen next year, which then means the LHC is going to be off for about 3 years, maybe 4 years. And that also means if you come to visit, there's a slightly higher chance that you are going to be able to go underground. It's never guaranteed, I'm afraid, because we have so many people that want to go underground. But when we're off, then we'll have slightly more tours, which will be great. So we'll be able to go underground a lot. It depends also on the maintenance of the cavern, if they're doing a lot of, because it is a work site. So if they're doing a lot of work, then we won't be able to have tours. But should be a lot more ability to go underground, which will be very exciting. And I saw somebody asked also close to that, do I give tours to Atlas or other places? So a lot of the time I give tours in Atlas because that's the experiment I work on the Atlas experiment. But I give tours at the CERN Control Center. So that's the control room that controls all of the accelerators that we have at CERN. I like to do the Antimatter factory. That's a very cool place to visit. That's above ground, and you can go and see that any time of the year. Which is a really interesting place to go and visit because we make antimatter at CERN and we study it. And there are whole experiments here at CERN that are doing that work, which is really exciting. And yeah, we've got a bunch of other places that you can visit as well. So I tend to do Atlas. I don't tend to do the other experimental caverns. I will also tell you a little secret. it's not just because I love Atlas, it's because Atlas is very close and so I can go there very easily. CMS is on the other side of the ring, so I do feel for my CMS colleagues who have to travel to the other side of the 27-kilometer long accelerator to get to CMS. LHCb and Alice are nice and close by, but I don't work on those, so I'm not as much of an expert, and my colleagues in those collaborations can tell you way more details about those. And what I'm hoping to do in the future is also buddy up with some of the other experiments and go and do some live streams or some filming in the other caverns and with the other experiments and show you more about what's going on at CERN as much as I can, basically, is my plan. So I have missed a bunch of, how is the antimatter made? I've missed a bunch of questions, sorry. And in a minute, we're going to go for a wander around this garden. Let me give you a sneak peek of what it looks like. So that's my iPad. So we're going to go and look at this. We're going to look at, you didn't see it in my where I was sitting, but this is Gargamel. So we're going to go and have a look at that. This is my favorite sort of, it's not a detector, favorite sort of statue, but it is a former working piece of equipment at CERN. And I'm going to go and show you that. So we're going to go have a wander around the garden in a minute, which will be very nice and is the whole reason that I'm here. I'm going to drink some water because I did not drink enough water today. I went on a lunchtime run and now I'm dehydrated. It is a very beautiful garden, yeah, I agree. So yeah, thank you so much for joining me on this live. I really appreciate you coming to hang out with me on this Friday morning, afternoon, evening, wherever you are. So yeah, somebody asked, how do we make antimatter? Well, actually, antimatter is pretty easy to make. Even your avocados and what else makes it? Bananas make antimatter. So if you have anything with a lot of potassium in, then the sort of radioactive decay that happens in those, well, bananas are a fruit, avocados are a fruit. I'm a physicist, not a biologist. I don't know. Somebody tell me what an avocado is, please. But anyway, it's a food. They have potassium in them, and they the potassium has a process where antimatter is produced in it. So if you've eaten a banana or an avocado today or something with a lot of potassium in, there is a chance that antimatter is being made inside of you, just a tiny, tiny, tiny amount. So it tends to happen in radioactive decays, radioactive processes, and it happens in our accelerators. When we collide the protons together, we can get antimatter being formed in those collisions, and we see quite a lot of it, but none of it hangs around. It will annihilate very quickly as soon as it interacts with a matter counterpart. Then it will just annihilate and fizzle away into photons. So yeah, a positron or two will get produced. But we have an antimatter factory where we take, for example, we can take the protons, we hit them into a target, then it produces antiprotons, so the antimatter counterpart of protons, and we can capture those because the very nice thing about antiprotons are that they are charged. So things that are charged are nice and easy to capture, or easier to capture. And then we slow them down in an accelerator, but it's a decelerator, so it is exactly the same setup as a regular accelerator, but we have the fields inside are going at a slightly different timing so that you slow down the particles instead of accelerate them. The best way to explain this that I have is that if you're sitting on a swing and somebody pushes you from behind, and if they push you at the right time, you'll go higher and higher on the swing, right? But if they mistime their pushes and they sort of put their hands against you as you're coming back, then you'll slow down. And this is exactly how the decelerator works. So it's the same process, but slightly in reverse, and it will slow down those antiprotons, and then we can capture them in experiments. And we also make anti-electrons that are called positrons, and they've been able to make anti-hydrogen. And they do a lot of studies in the antimatter factory to study the properties of antimatter, and especially things like anti-hydrogen. We know hydrogen very well. This screen is, it's not very straight. Also, I'm not sitting up straight. We know hydrogen very well, so then you can study the anti-hydrogen and see then if its properties are what we would expect from hydrogen, because there should have been in the very early universe equal amounts. This is what we expect, we think, equal amounts of matter and antimatter, and we don't see a lot of antimatter around in our universe. And so there are a number of different experiments. We have the Antimatter Factory here at CERN. We have AMS up on the International Space Station, and they are trying to understand. We have LHCb, of course, which is one of the 4 main experiments on the Large Hadron Collider, and they are really focusing on this question: where did all the antimatter go? And what is the difference, apart from charge, between matter and antimatter that can help us understand where it went? So there's tons of great experiments. Do you think a powerful mass destruction explosive can be built with antimatter? I'm going to qualify this and say yes, but no. So if you had enough antimatter, sure, you can make a lot of energy, because when antimatter and matter come together, then there's quite a lot of energy from that annihilation. But we have made such a tiny amount at CERN, and being able to capture it and hold it. So if you've seen Angels and Demons, where they have a little vial with antimatter in it, and it's part of the plot device that this is going to be used for nefarious purposes, that would be really difficult to do, because as soon as you run around with your little vial, it's already going to touch the sides of the wall, which is made of matter, and it's already going to have annihilated. So maybe you could make it, but you couldn't collect. So you couldn't collect enough. You couldn't transport it around. I mean, we've been working on transporting antimatter at CERN, and we put it in a truck, and it goes quite slowly, and it's very impressive. It's good work, but it's not going to do anything bad. What would be really interesting to use that kind of amount of antimatter for is for transport. So one of my favorite things in sci-fi is when they use antimatter in spaceships, which I think is a very cool way that we could power spaceships, but really being able to store it, because as soon as you get a little bit of movement around, if your antimatter is touching matter, then your fuel is going to end up not helping the ship go faster. So no is the sort of, for now, answer. Okay, I'm going to show you around this garden and show you some of the beautiful detectors that we have, and also accelerator parts, and then we can do some more questions. So yeah, let's have a bit of a walk around. I'm going to leave my stuff here because we're at CERN. So if any of my colleagues are watching, my bag is unattended. Okay, so we're going to walk around, but I'm going to try and not get people walking past in the camera because they haven't agreed to be. So hopefully you can all still hear me. Let's go back down so I can also see the comments. Oh yeah, so somebody said antimatter is very expensive. So it is very expensive, and therefore not a very efficient use of it. It's much better using it for science. So this is Gargamel, which was a bubble chamber at CERN. So this is an actual detector that is now hanging out in our Detector Garden. I'm going to see if I know I can't zoom out on my camera. It does have a wide lens, but we can't use it on here. So it was a bubble chamber, and then, oh, has this got a window? It does not have a window, so we're going to try and avoid the spiders. I will show you inside this detector. It's a little bit, you know, it has been outside for a long time. But we can go inside the detector. Hopefully you can still hear me. I've got my microphone on, and have a look around. So I was reading the questions as well. So yeah, this was a bubble chamber at CERN, and the bubble chamber means that you could see the particles inside of the detector. So that's why it's got a load of windows, because you could take pictures of them. I'm not tall enough to, shall we stand on this? That sounds like a terrible idea. Let's have, oh, okay, there we go. I don't know if you can see inside. Oh, there's a spider on there. Oh no, it's a, ooh. Okay, this is not science content, but I think I saw a hornet. Let's not get too close to that. Okay. So this is a bubble chamber, and it was used at CERN in the 70s. So we can come and have a look at this nice piece of information that tells you about it. So it was used in the 70s, and as it says here on the sign, it was used for one of CERN's major physics discoveries. So what we call the neutral current. So it was a new kind of particle interaction, And yeah, I'm reading from here because this explains it very nicely. So this detector was filled with 18 tons of heavy liquid, so freon or propane. And then, as I said, you could see the bubbles as the particles were passing through the detector, and they took pictures. And then we had people called scanners. So these were most often women, almost all women at CERN. And so they would then look at the pictures and they would work out the momentum of the particles and do the calculations of the pictures. Sorry, there was a sound over at the side. And so this neutral current then led to the later discovery of the Z boson here at CERN. So it was sort of the first information about the Z boson. Yeah, somebody says in the comments, astronauts get flashes in their retinas from particles hitting them. So I think that's about particle interaction in your eye. So you can, yeah, sometimes see detectors, sometimes see particles. That's what and also you can see photons. So we can see some particles. Getting slightly distracted. So I'm gonna turn this around because actually I was climbing on that chair to show you inside of the detector when really I could have come around the other side and shown you much better the inside of this detector. So yeah, this was a detector. Oh, there's that hornet. I don't know if anybody wants to see that. It's making a lot of noise and we're going to move away from it. As I said, I'm a physicist, not a biologist. So this was used for a major discovery at CERN. And talking of bubble chambers, let's go and have a look. This one looks like a spaceship. I love looking at this one. I'm going to walk backwards very carefully so you can get a good view of this detector, which is now outside and is a statue at CERN, but again was used for very important physics research. Somebody says please be careful. Yeah, I moved away from the hornet and I also managed to walk backwards without falling over, so thank you very much. Let's have a look inside of here. So yeah, on the sign it says it looks like a moon lander, which it kind of does. So we can go underneath. Oh, I just looked at the sun. That was a bad idea. That's my sunglasses making a very pretty light on the inside of the detector. So this was also a bubble chamber, and this had 30 cubic meters of liquefied gas, and it also recorded the interactions of elementary particles. And again, you would then take pictures of those interactions, and then you would have to sift through all of those pictures, which was often done by women called scanners here at CERN. And so they had pistons, which I think is perhaps linked to this part over here, which is very cool. And every time the piston expanded, then a photograph was taken. And it was operated between 1973 and 1984, and it produced 3,000 kilometers of film. That is an incredible amount of film and so much data to go through. So if you're just joining, somebody asked what this is. It's a bubble chamber. So it's a very early form of particle detector here at CERN. It was used in the 70s and 80s to take pictures of elementary particles before we had more digital methods in order to be able to study the particles. So it's a bit of CERN history, and we can see it now today out in the Detector Garden. So this is where I am right now. I'll just give you a little sweep around the garden. This, if you haven't seen, is part of the Science Gateway at CERN. So this building we're looking at here, we have a brand new museum, which is on the other side of the road. And then actually, yeah, it's also, I think, in this building too. And you can come for free to CERN and visit our museum and come on tours. So we do tours at CERN. And any day but Mondays, don't come on a Monday because we will be shut and you will be disappointed. So let's have a look at another piece of, so this is the piston. This is the piston. I was pointing out the wrong bit on the other thing. This is the piston for this, which is incredible. So if you do have questions, please do put them down in the chat. And right now we're having a look at the nice things in the garden, and then we'll have another chat again afterwards answering questions. So yeah, let's have a look. This says it pumped 13 million times over 11 years, so about 3 times a minute, each time exerting a force of 350 tons. So it's at the foundations of the BEBC went down 20 meters because of the force of the piston going up and down. And so yeah, each time the piston released its pressure, then the liquid inside the chamber boiled. And so then when a charged particle passed through, it would leave its bubbles. So that's how this bubble chamber was working, that you would have a piston that would then create pressure in order to, yeah, this does look more like a piston. Yeah, I don't work on cars. But yeah, it would then create pressure, which would then liquefy, no, it would then boil the liquid inside of the detector, and then you would get little bubbles forming where charged particles pass through, which is a very fancy detector. So this is what we have here at CERN. So now I'm going to wander over, and I told you this was my favorite. And if I could have one of these in my garden, if anybody from CERN is watching who has a spare one of these, I don't have a garden, so I've got nowhere to put it right now. And to be honest, I get to look at it every day at CERN, and I get to look at it every day at NICF, because we have one outside of our building in the Netherlands where I work. So I do get to look at them very often. But if I ever have a big enough garden and there's any of these going spare, I want one of these in my garden. So this is, let me tell you what it is. So we're going to go stand over here. So it is the, it's the radio frequency cavity for LEP, which was an accelerator before the Large Hadron Collider. So it was in the same ring as the Large Hadron Collider. So it was, yeah, the ring, the tunnel is 27 kilometers long. And it had the Large Electron-Positron Collider before we put in the Large Hadron Collider. So this tends to be the way that we do things. We start with the lepton collider because leptons are elementary particles. They are the, let me turn around so you can see me too. So leptons are elementary particles. They cannot be broken into any smaller pieces as far as we know. And then hadrons have quarks and gluons inside of them. But because well, they do. Protons are hadrons, which have quarks and gluons inside of them. And because they are more massive, it means that we can go to higher energies. But then because they have stuff inside of them, it's a little bit more messy. So we have these compromises where we choose the type of particle that we accelerate in an accelerator, depending on what technology we have, what we're trying to study, and then the limitations on the size of the accelerator, which then limits the energy that we can get to. So I'm going to turn this around again so you can look at this cavity. So it was used to accelerate the electrons and the positrons, and it produces microwave oscillations, microwave electric oscillations. So this was at 352 megahertz. And so the electrons and the positrons, like in the Large Hadron Collider, they were grouped into bunches. And so they would time, so yeah, here it says, I'm reading on the very nice, we have some information, which is aiding my description for you. And it says here that it's like beads on a string, but if you think of beads on a string, you think of the string that's in between them. I like to talk about it as a train, but then if you think of a train, it's still connected. But they're bunches, and they're separated in the beam of the accelerator. And so then you can time the pulse of this cavity to push, again, the electrons or the positrons at exactly the right time. So earlier I was talking about decelerators. This is an accelerator. If you time it at just the right point, then it will increase the speed that these particles are traveling at. And yeah, it would only use the energy between the passage of individual bunches, and that saved some energy as it reduced the heat in the cavity. So we can get up nice and close. And I just think this looks really steampunk and is very cool. And I would love to have one in my garden. So as I said, this was used to accelerate the electrons and the positrons in the Large Electron Positron Collider, the LEP collider at CERN, which was running in the 80s. And it was the predecessor to the Large Hadron Collider. Okay, now we're going to go over here. This one I will try to explain to you, but it's a little bit out of my field. So now we're more in accelerator physics rather than detector physics. But it is a very cool device. Again, it looks super steampunk. So this is, it's also part of the accelerating process. So it has capacitors inside of it and rectifiers. And it's an electrical staircase. So basically at each point along the accelerator, someone says that looks like high voltage. It was high voltage. It was 500,000 volts to drive the particle injector. So basically at each point, it would increase the energy as it went up and up and up. And then it would get passed along to this part of the accelerator. And it's so massive, I've got to step back. So then this is the point where particles got their first kick before then being injected into another part of the accelerator. And it was the first, if I understand correctly, it was the first way to accelerate. I've got to keep going, I'm still working backwards. The first way to accelerate protons at CERN, which was a huge achievement. What I will do in the future is I will bring an accelerator physicist here to talk to you as well, because that is definitely, they can tell you lots more interesting fun facts about how this all works. But it's basically a huge proton accelerator. And it's just a very nice evening that I thought I would come and show you this garden. So let's go look at the sign again to make sure I've told you all of the fun facts about this. Well, my favorite thing is it's known as a flip-flop circuit. So yeah, it's a zigzag arrangement, and it doubles the effective voltage input from a transformer. And so then it had 500,000 volts, which drove the particle injector. And in 1932, so Cockcroft and Walton in Cambridge used this technique to accelerate protons for the first time. So maybe it wasn't the first time at CERN, it was the first time in Cambridge, sorry. And the ingenious capacitor rectifier arrangement, also known as the flip-flop circuit, became a standard feature of binary logic for digital computers before the invention of transistors. Yeah, so the garden's much nicer now. So Vasco is saying that when they were writing their thesis here at CERN last year, it was all construction site. And that is because, so it used to be a construction site here because they were building, we've lost the Science Gateway in the background. And so this used to be part of the previous museum that we had here at CERN. And now it is an open garden for the CERN site because the museum we have is behind this giant accelerator piece back there. But it has other detector components now in that museum. So there's lots of other cool fun stuff to see. But now you can't come and visit this detector garden, so I thought I would show you around during this live. So yeah, I really love the LEP cavity. That's still my favorite. This one looks like a spaceship, even though it's not. I'm going to be very clear, it's not a spaceship. And then this one is a huge part of science history here at CERN, with the discovery of the neutral current. And then later, the W and Z bosons were detected by a different experiment and a different setup. But this was sort of the lead-in to those discoveries. Right, now, I'm going to come and sit back here, and hopefully that hornet's not hanging around. So hopefully you enjoyed our tour of the Detector Garden. Let's have a few more questions, I think, if people have some more questions. I did not manage to, I see there's some in the chat that I missed. But if you have more questions, then let me know, and we can hang out for a bit longer, and then I'm going to go home because I need dinner, because I keep doing these lives when I haven't eaten food. And I would like to go eat dinner in a bit. So there's a question Any particle story in the earrings? No, I would love more physics themed earrings. But these are ones my mom gave me a very long time ago, and I just think they're very pretty. Thank you. There's a nice comment saying that I'm a great guide. I appreciate that. I know a lot more about the detector side, and I know I say some about the accelerator side, but I do want to interview an accelerator physicist. So if later anybody from the accelerator field is watching this and wants to come and hang out with me, please do feel free to let me know. Oh, what does my shirt say? So it says, smash particles and patriarchy. So it was a t-shirt that was produced by a team called Physicists for Inclusion in Science. And I really like the message. And the t-shirt looks cool. Thank you. Somebody said they love these lives. I really appreciate that. I really like these style of lives because it just feels like we're hanging out and chatting about physics and other things at CERN. And it's nice that I can just hop on and we can hang out like this. So, how do you load protons into the beam? Do you scoop them in like Skittles? I wish that would be so cool. That would be such a cute way. Now I'm imagining like all these different colored proton Skittles being fed into the accelerator. They come from a hydrogen gas bottle. So hydrogen, one of the most, but not one of, but the most abundant element in the universe, is a proton and an electron in its most common form. And we take the hydrogen gas and we can, so usually when I tell this story, I say we just strip the electrons off. Actually, we have a nice process where we add extra electrons in to make them doubly charged, which then makes it easier to focus these doubly charged, are they doubly charged? No, because they're neutral. So, well, then they're negatively charged if you add in the electrons. And then you can better focus the gas beam before you then strip all of the electrons away, and then you have the positive. Just the protons left over. So it's a bit of an extra technique, but essentially you eventually remove the electron from the hydrogen and you're left with the protons, which are nicely focused, and then they go into a bunch of pre-accelerators. So we start with a linear accelerator called a LINAC, and then they get a little boost in energy, and then they go through a series of bigger and bigger accelerators at CERN, which were actually built originally to be an accelerator on their own. And then as we built larger accelerators at CERN, we then use them in the chain to get to higher energies. And then sometimes they also do other jobs here at CERN. And eventually we go to the Large Hadron Collider. So they start off at 450 GeV, which is a unit of measurement, which is a billion electron volts. And then they get up to 6.8 TeV in energy. So then that's a trillion electron volts. And so yeah, they get accelerated them up. Yeah, somebody's saying I'm now imagining science-themed Skittles. So Skittles, if you're watching and you would like to make some science proton-themed Skittles, then we can also talk about that too, because I am a fan of Skittles. They're not watching. Okay, just take a spoonful of protons and let them slide into the accelerator. Now I've got Mary Poppins in my head. Just a spoonful of protons make the accelerator go round. I'm not going to sing for you because I want people to stay in the live. If you are watching and you are not subscribed already, please do subscribe to my channel and come hang out with me in future lives where we can talk about physics and have wanders around sites at CERN. So one of the cool things about CERN is there's no filming restrictions. So I get a lot of people asking me about stuff at CERN, and yeah, there's no filming restrictions. We can just, oh, there's a bird that landed on the lip. Do I want to show? I mean, it's a little bird. I'm easily distracted, sorry. Oh, we zoomed in too far. There we go. Isn't it pretty? Like nature and science hanging out with each other. Okay. No. Oh. We'll leave the bird to its afternoon. Yeah. If you want to subscribe, you can subscribe. That would be great. And yeah, I think you can like the live stream. Maybe I should be encouraging you all to like it more as well. And that would then help it get shown to more people, because YouTube will then send it to people, I think. So Vasco is asking about like ending the stream and it's in the evening and I have to get home and make something to eat. It'll be a long time till you get something. I have a bike, so I can get around pretty speedy. It's an electric bike, so it gets me home pretty quick. And yeah, I haven't worked out what I'm doing for dinner, but I didn't eat all my lunch accidentally because I'd scheduled too many meetings today, even though technically today is not a holiday at CERN, but yesterday was a holiday at CERN. And what tends to happen in CERN is it Faire le Pont? Make the bridge, where we then, a lot of people take the Friday off. And I was going to do this, and then I thought, oh, but actually it's a nice quiet Friday and I can get a lot done if I don't take it off. And then I scheduled too much and I had a really busy Friday, which was very silly. But my teaching starts on Monday in Amsterdam, and so I want to make sure I'm ready for that. So I take a vacation afterwards. Do you guys conduct ion propulsion testing at the CERN facility? No. I mean, we accelerate ions, so I think technically that is propulsion, but it's the propulsion of the ions, not the propulsion of other things because of the ions. So no, we don't do that kind of research here. We're just accelerating things within the ring and colliding them together. We're very much about smashing stuff together. Here at CERN, that's our main research. So somebody was heading off. Thanks so much for joining. You probably already left, but thanks for joining. Which machine is your favorite at CERN you want to take home? If I could take it home, I don't know if I want any of them in my home. They are all slightly radioactive. I think I like them underground, where I don't have to stand next to them. I want to take this one. I don't know if you were here in the stream earlier, but I want to take, not Gargamel, Gargamel's a bit big, but I want to take one of the LEP cavities, because there's like a, oh, I should know, we zoomed in too far. Not very good at this zooming, it goes very quickly. This is one of the LEP cavities, and it was used to accelerate protons and electrons in the LEP accelerator, LEP collider here at CERN. And I would love to take one of these home, because there was about 1,000 of them, I think. I don't know the exact number. And there's a bunch of them everywhere. So if you go to a physics lab that was involved in particle physics research in CERN, there is a chance they might have one out in their lawn. And I don't know if we've got any spare. I doubt it. But if I could, and I had a garden, I don't have a garden, I would want to take one of these home. What I think we should do, and if anybody wants to do this, then we should talk. I would love to make little versions of these that you could then have on your desk. That would be very cool. But I have no idea how to do that. Maybe we could 3D print them and then paint them. That would be fun. Let's put the camera a little bit further away. I need to cut my fringe. That's what the basement is for. Yeah, I don't have a basement either, but we do have, like, Switzerland has a lot of bunkers. So you could put one of the experiments in the bunker. Oh, I tell you what I would have in my home though. There we go. What I would love to have in my home if I had space is a cloud chamber. So I've been talking about bubble chambers, which is this one behind me. This is Gargamel, which was involved in the neutral current discovery at CERN. And then this one, which is also just looks very cool. This is also a bubble chamber, which has a giant piston that we can see here that we were learning about earlier, that was used to boil the liquid inside in order to be able to do its experiments. I would have a cloud chamber, which is a similar kind of process in that you create an environment where when a charged particle passes through, then it leaves a little trace in either the cloud or the bubbles in the liquid. And you can then take pictures and look at particle interactions happening. And we get a lot of particles that are coming from space. So you have cosmic rays. These are mostly, I think, protons in the atmosphere that then collide with our atmosphere, but then other types of particles as well. And mostly it's muons that make their way down to us from cosmic rays, which are the heavier cousins of electrons. So you could you can see those in a cloud chamber. But then also there's a lot of natural radiation around us. People get a bit scared of the word radiation, but it's happening everywhere, all around us, all the time. And it's just, you should have a healthy respect for radiation, but not be too afraid of it, you know, depending on the situation. But then, yeah, there's also things like radon gas that's just around us, and there are rocks that have a slight radioactivity as well. And so you can see all of these particle interactions happening in a cloud chamber that you can build at home. You can even build one with a fish tank, some dry ice, and some alcohol. So you need alcohol vapor to make your cloud. Or you can get like a more complicated one that has a proper cooling setup. And it's really interesting to be able to see these interactions with your eyes, because even though Atlas is an amazing detector, and the other detectors we have here at CERN are really incredible, and they're custom designed detectors that take thousands of people to build them, and we have to run them, and I love them, you can't see what is happening in the Large Hadron Collider with your very own eyes, and you wouldn't want to stand next to it anyway. But it's just so interesting when you have a cloud chamber. So if you are a teacher and you want to show your students, if you're in high school, you can build a cloud chamber in your high school and show your students particle physics happening right around them all the time. So that's what I would, that's a great question. That's what I would have in my home, is I would have one of the ones that's sort of not cooled with dry ice because you have to replace it, but you can have proper cooling. And I would have a cloud chamber in my house that I could just look at all the time. Oh, somebody's asking, can you explain the graviton? So the graviton is a hypothetical particle. So we have not discovered it. There's no evidence for it yet, but it's proposed to be the particle associated with gravity. So we have the photon, which is the particle that is associated with electromagnetic force. It's the particle of light. It's how we see each other, and a whole bunch of other stuff like radio waves are photons. And then we have the W and Z bosons, which are associated with the weak nuclear force. I was talking about the neutron neutral source with the Gargamel, and they are involved in like nuclear reactions. So they are the reason that the sun shines, so we wouldn't exist without those particles. And we have the gluon, which is associated with what we call the strong force, and it's one of the few things we named correctly, because it glues the protons and neutrons together, and it glues the atomic nucleus together. So it's the force and the particle associated with that force holding them together. But out of the four forces, so the electromagnetism, the weak nuclear, the strong force, and gravity is the only one that doesn't seem to have a particle associated with it. So there's a hypothesis that there is something called the graviton, and if we discovered the graviton, that would be very interesting. We do look for it at CERN, but there's been no evidence for it so far. And there's a lot of there's people that say that maybe gravity isn't the same as the other forces, and it doesn't have a particle associated with it. And that would be okay too. I mean, we don't get to choose how the universe exists. We just get to study it and learn as much as possible. Somebody says that RC Lifeon did a video making a DIY cloud chamber. It was pretty cool to see, and it made it relatively easily, and the actual reaction. So yeah, you can just make them you can get a fish tank and make one at home, which is very, very cool. So someone says, my favorite machine is the LHC, and you were the first where I got to know about Atlas. So thank you very much. I am very happy that I got to share that information with you. Oh, somebody says, do you think we're more likely to find evidence for gravitons or tachyons? Honestly, I think we're way more likely to find evidence for a graviton before we discover anything to do with tachyons. Tachyons, so I'm not a theorist, so I don't work on this every day. To me, they just feel like a little bit, they feel sci-fi, they feel like an add-on, because it's about time going backwards, right? And it's always used in sci-fi when they want to do time travel. They just like, oh, the tachyons did it. Okay, not always, but it's often they'll talk about tachyons with time travel, and I think it's way more likely that we'd find a graviton before we found a tachyon. one of the few things we named correctly. Yeah, we're not very good at naming things. I mean, to be fair, we called one particle a strange particle because we had the up quark and the down quark, and then they were like, and now some strange stuff is happening, and so then they just called it the strange particle. And then they realized that they were kind of paired, so we have the up and the down, and then the strange has a partner, and so they thought, okay, well, what's the opposite of strange? And so then we named it the charm quark because it was charming. And then there's two communities. Hopefully this microphone isn't getting scratchy. There's two communities, because then the next set of pairs that we have in the standard model, you either have the top and the bottom, or truth and beauty. And what I find really interesting is people who tend to work on top quarks, like me, call it the top quark, and then we have the bottom quark that pairs with it. And people who tend to work on the bottom quark don't like to call it the bottom, so they tend to call it the beauty quark, and then they have to talk about truth. But I honestly, I don't love the name truth for a particle. I think it's a bit pretentious. I don't mind beauty, it can be beautiful. So I like the top as the description. But yeah, we're not very good at naming things. We're pretty bad at it. Bad at it in particle physics. A particle to fill plot holes. Yeah, exactly. So there was a good question earlier about quantum. Sorry, I missed. Oh, I got distracted by this one. Is it dangerous to work there at CERN? Like the experiments you do can affect your health negatively? So let me talk. So the short answer is no. It's not dangerous to work at CERN because we do not work next to the detectors most of the time. Nobody is underground when the LHC is on. And I wear a dosimeter a lot of the time when I'm doing work on the detectors, and it doesn't register anything above background level. So it is more dangerous to go in an airplane because of the radiation. Airplanes are very safe to travel in, but when you go higher anyway, if you go up a mountain, then you just get exposed to more of those cosmic rays that are happening. And it's more dangerous to get an X-ray, but those are medically necessary. And so it's just part of radiation that it's around us all the time. We have to live with it. We just have to manage our exposure to it. And my exposure at work is the most dangerous part of my job is when I go up in an airplane and get exposed to cosmic rays. I get way more radiation from all of my travel that I do than I get from working day to day in a radioactive environment. Everything's very safe. We have a lot of radiation monitors. I carry a dosimeter when I need to. We have active dosimeters if there's ever a risk that we need to be alerted right away about radiation. And there are a lot of regulations about how much radiation a worker can get working in a radiation environment. And so the reason I hesitated ever so slightly is because there are situations where a worker will need to be exposed to slightly more radiation. But this is then a calculated decision, and there are limits on how much a worker can get over their lifetime, or in a year, for example. And so everything is a slight risk. Eating meat, and I don't want to have a whole conversation about it, but eating like processed meat has a risk associated to it. There are certain things where it's just statistically you have to manage your risk. And so we have radiation, so I'm not going to say that there's absolutely no risk at all, but it's very well managed, it's very carefully controlled. You cannot go underground. It's absolutely impossible to be underground while the LHC is running near the LHC, because we have doors that measure our irises. So first of all, you have to be authorized to go underground. And as soon as, if you forced that door to get it open, to be able to get to the elevator that would take you underground, as soon as that interlock is broken, the beam would be removed from the cavern before you would even get to press the button on the lift. So it's so very safe. And then there are people monitoring and everything. So no, it's not dangerous. There's absolutely no, I spend almost all of my time around at CERN and near, like above the accelerators, and it's background radiation. So yeah, there was a question I was trying to find the question about quantum that I lost. Yeah, so a quick one I can answer is when you switch it on, how long does the LHC take to boot up? So, I mean, the LHC, it depends on depends what you define by boot up. At the beginning of the year, first of all, we have to cool the Large Hadron Collider magnets down. So we cool them to very close to absolute zero. It's 1.9 degrees above the coldest temperature in the universe, which is about minus 270 something degrees centigrade or degrees Celsius. And so first of all, they have to be cooled very, very cold, and that takes a while. And then we have to make sure that they're performing as we want them to. So basically, there's a whole number of steps called the commissioning phase, where we have to check everything is running as we left it before the winter, and that can take weeks. So we slowly go through all of the steps and approve everything for the accelerator, and then we have to ramp up the intensity, so how many bunches we also have in the beam, and that, yeah, as I said, that takes weeks. When we've been running regularly and we dump the LHC beam and then we want to refill again, it takes about an hour and a half to get it all the way up, because we have to reduce the strength of the magnets, and then we feed the protons in. They go through the pre-accelerators, they get accelerated, they go back into the LHC. We have to ramp the magnets up to the strength that we want them at, so that the beam is at the energy, and then we start colliding again. And that takes about an hour and a half, which is very quick, which is great. I've lost the comment about quantum, I'm sorry. So if you want to ask it again, please do drop it in into the chat. I saw a comment about old chill, and I realized that was because I was talking about how things that are cold. Oh, somebody's asking about internships. Yes, we have lots of internships. Please apply for them. Yeah, and there's a comment, the most dangerous part of working at CERN is like on any other construction site that you could lift something heavy or something falls on your foot. And that's why when we go underground, I wear a helmet and wear steel toe-capped boots, because the most likely way I'm going to get injured is by dropping something on my foot. And that's why we have safety equipment for that. Yeah, so the question is, could you talk a little bit about quantum theory and how it might connect to particle physics? Quantum theory is intricately, deeply connected with particle physics. The collisions that happen, we cannot choose exactly what particles are created within the collisions. It's quantum mechanics deciding what is happening, and so then we just have to measure over many, many, many collisions to work out what is happening in the comments. Just going to remove comments about my appearance, because we're not having that. So quantum field theory is particle physics, exactly. So it's they're part of the same theory, deeply connected. And there's a question here. Back in 2012, you want to ask what happened when the Large Hadron Collider, so you found the God particle. This is what it's commonly called, but we call it the Higgs boson. The God particle was like a nickname that came about because of Leon Lederman, who was a Nobel Prize winner. He wrote a book, and I'm not sure I can say the name of the book, but he wanted to, I think I can say it, it's fine, right? He wanted to call his book The Goddamn Particle because it'd been so tricky to find. And his publisher said, no, you can't call it that. You were not allowed to call your book that. So they took off the second part of the word, and they called it The God Particle, the book. And then that nickname kind of stuck, but we call it the Higgs boson. So just as a little bit of an explanation. So it was discovered in 2012, but the thing is, we didn't just discover one and then announce it right away. We collected all of the data from what we call run one, so all of the previous years that the Large Hadron Collider had been running, and the ATLAS and CMS collaborations collected all of this data. And what we did is we were looking for the Higgs boson, but we didn't know what mass it would have, and we only knew some of its properties. We didn't know all of them. And we were looking at a number of what we call channels, so ways that the Higgs boson could change into other particles, because when it's created, we never directly detect a Higgs boson, we detect what it changes into. And so we were looking at all these different ways that it could have been produced in our detectors, and then we were looking for slightly more data in those processes than were predicted by the simulation without the Higgs boson. So we collected all of this data, we did all these comparisons, we had to calibrate the detector, we had to make sure we were understanding everything correctly by looking back at particles we discovered before, and are they behaving in the way that we think they should be. And then in 2012 we had enough data and enough different ways that the Higgs could change into new particles, and we were seeing what we call an excess, a little bump, and we put all of that data together, and we have these thresholds in particle physics where we can start to be more confident. So we talk about 3 sigma, which is a statistical way of saying how confident you are that what you found is actually something and not just statistical noise. And once you hit 5 sigma, then you have a 1 in 3.5 million chance that this would just be statistical noise showing up in your detector. And by that time you think, okay, this is very likely to be true. And not only did Atlas see it, but CMS saw it too. And so then we were so confident that we could say we'd discovered this brand new particle. And in 2012, we had the announcement to the public where Atlas and CMS finally told each other what they had, and we announced to the world that we had a new particle. So 2012 was the announcement, but we had been studying it for years before. And it wasn't only at CERN, we had been looking for this particle for 50 years or more, ever since it was first proposed by Professor Peter Higgs and Professor Francois Englert and a number of other theorists. So those were the 2 that got the Nobel Prize for it, but it was 6 theorists in total who had been working on predicting the Higgs field, or the Braut-Englert Higgs field, as some people call it. And then we looked for this particle, but we didn't know what mass it had. We didn't know what accelerators could produce it. And so it was a really long process in order to be able to search for this particle. So I can see people in the chat that I recognize. Thanks for joining. Does Atlas have different detectors for all the different particles? What are the particles that are directly detected? Max, that's a great question. We have 3 main sub-detectors in the Atlas experiment. We split them up into, generally we have the inner detector, which is used for tracking charged particles right from the very heart of the collision. So if you think of a giant cylinder and inside there are a number of different layers, and the very heart of this cylinder we have the inner detector, and this is very similar to the sensors that you have in your mobile phone for your camera, and it tracks charged particles as they pass through. And then after that we have something called the calorimeter, and the calorimeter measures the energy of particles by them depositing their energy in the detector, and then it's measured out as a signal. And then the muons, which are the heavier cousins of electrons, they tend to travel to the outside of the detector, and so we have a whole section of detectors just for them. So each detector doesn't only measure one particle, except for the muon detector, but what it does is each particle interacts with either one or more of these detectors in a unique way, allowing us to be able to identify them. So for example, an electron would leave a track in the inner detector, and then it would deposit its energy in a part of the calorimeter in a certain way that allows us to say, okay, that was an electron. And then we also have very strong magnetic fields in the detector, and that allows us to then measure the momentum of the particles, which tells us a lot about the process as well, and determine what charge they have, because a charged particle will bend its path in an electric magnetic field, and then we can say, well, this one was positive or this one was negative, and that tells us more information. And a detector is like an onion. It has layers, exactly. So thanks so much for joining. I see some people leaving. Yeah, I think I'm going to have to wrap this up because it's been over an hour. Usually I try and keep these to no more than an hour, but it's been really fun chatting with you today. And it's a beautiful sunny day. Well, it's not sunny anymore. Oh, it is sunny. The sun hasn't set yet. But it's a beautiful day here at CERN. if you look at all these tables, by the way, it's not that I'm a loner and sitting out, well, I am sitting out here by myself. We have a restaurant over in that direction where people are having beverages for a Friday evening and maybe some food, and it's very sociable. But I wanted to come and sit out here where I wouldn't disturb those people having a nice Friday evening while I'm chatting to you loudly, talking to my phone. But one time I am planning to do a live out there where I can just ask some colleagues to come hang out and we can chat together, which I think would be really fun. So I think, yeah, we're gonna wrap this up. I'm reading the nice comments. Thank you so much for joining. If you're not subscribed, please do subscribe. I'm really trying to grow my YouTube channel and I want to share particle physics with as many people as possible. And I hope that you've enjoyed this live. Thank you so much for your questions and hanging out with me. I really appreciate it. I really enjoyed it. And I will see you in the next one. And have a wonderful Friday or Saturday, if you're already in Saturday, wherever you are. And talk to you next time. Bye.